I think we have to start with what is, one of the oldest and most fundamental puzzles in modern machine learning.
Hmm.
Why do these incredibly complex multi-layer neural networks actually learn hierarchical functions so well, especially when we're just training them end-to-end with something as seemingly simple as SGD?
It's the core theoretical gap, really. We know deep learning works, but the why it extracts these layered representations efficiently instead of just getting stuck in some awful local minimum, that's been a mystery for a long time.
So that's our mission for this deep dive. We're going to unpack the answer proposed in that landmark paper by Allen-Zhu and Li, Backward Feature Correction, how deep learning performs deep hierarchical learning.
Right. And to set the stage, when we talk about hierarchical learning, we're talking about efficiency.
It's about taking a really complex function, g of x, and representing it as a sequence of simpler functions, h1, h2, and so on.
Exactly. And the whole goal is to drastically reduce the sample complexity, the time complexity, compared to just trying to learn that entire function in one shot.
And the paper's big idea, its central principle, is something they call backward feature correction. BFC for short.
EFC, yes. It's really the secret sauce, they argue. It's a dynamic mechanism.
Okay, so what is it actually doing? What's the punchline of BFC?
It's all about how the network handles errors. When you train all the layers at the same time, any imperfections or overfitting that happens in the early layers isn't permanent.
It's locked in.
It's not locked in. The BFC principles is how the higher level layers, while learning from those maybe flawed features, send corrective signals gradients back down. These signals basically force the lower layers to clean up their act.
So they automatically refine and correct themselves.
Yes, and that's enables the whole thing to converge efficiently. It's this continuous correction process.
Which feels intuitive, but the paper argues this is precisely what separates deep learning from other methods that just fail.
Right.
Let's start with the representation argument, because that's the classic one. We know deep nets can represent almost anything. You can model a super high degree polynomial as just a cascade of simple quadratic functions. But the paper is very clear. Capacity is not efficiency.
Absolutely. Just because you can represent a function doesn't mean you can find that representation through optimization. I mean, if the path is impossible or needs 1 trillion data points, who cares about the representational power?
Right, like trying to learn parity functions, where
Yeah.
things just get exponentially harder.
Exactly. And this leads to the most obvious failure case, layerwise training.
The one that seems so logical on the surface, just train layer 1, freeze it, train layer 2, freeze it, and so on.
Yeah.
But the paper shows, I'm thinking of figure 7 here, it just completely breaks down. Why?
It boils down to this idea of overfitting to high complexity signals.
Okay, unpack that.
So imagine your target function has 2 parts, a big, simple, easy to learn component, and then a tiny, noisy, high frequency component.
Okay.
If you train that first layer until it converges, it has to satisfy the entire objective function. It sees both parts.
Ah, so in its attempt to get the loss as low as possible, it tries to bake in not just the simple signal, but also some of that complex stuff.
It's too greedy. It pollutes its own features by trying to account for complexity that was really meant for the deeper layers to handle later on.
I think they have a great toy example for this. Something like g of x equals a simple part, plus like 0.1 times a complex part squared.
Yes, that's the one. The first layer, if trained alone, will distort its features trying to capture a piece of that tiny 0.1 term just to nudge the loss down a little.
And once you freeze that layer, it's game over. The deeper layers can't go back and say, hey, wait, you got distracted. That was my job. You've corrupted the foundation.
They're stuck. They're building on a compromised feature set. And that's the failure of sequential training. So this tells us that simultaneous end-to-end training has to have 2 things happening at once.
Okay, what are they?
First is what you might call forward feature learning. A higher layer learns simple combinations of the features that the lower layers have already learned up to that point.
And the second, more important part, is the backward feature correction.
That's the key. The higher layers are learning at the same time, so they start to figure out those complex signals. And as they do, the gradient they pass back down effectively subtracts that complexity from the lower layer's job. It corrects the initial error.
It's an iterative refinement, a negotiation between layers.
A negotiation is a great way to put it. It's a dynamic that layer-wise training just completely severs.
This is where the paper's empirical evidence really shines. They have this incredibly simple but powerful toy experiment on AlexNet that, for me, is the smoking gun.
Figure 2, it's a brilliant setup. First, they froze everything except the first convolutional layer.
and train just that one for 80 epochs.
And just as you'd predict from the theory, its features converged, they hit a plateau, the quality just stopped improving.
And then the magic happens.
Then they unfroze layers 2 through 5 and kept training the whole thing end to end. And what happens?
The features in that first layer, which had been totally stuck, immediately start improving again. Significantly.
Right, and that proves the improvement wasn't just layer 1 finding a better minimum on its own. It was the higher layers figuring things out and sending those BFC signals back down to clean up the mess.
It's such a direct, beautiful illustration. They do something similar with wide ResNet on adversarial training, right?
Yeah.
How does that work?
That's figure 3. The idea is that if you only train the lower layers, their features become brittle. They overfit to these, high complexity signals in the images that don't generalize.
The kind of signals that adversarial attacks exploit.
Exactly. But when you enable full BFC, the higher layers learn to handle that complex adversarial structure. And in doing so, they effectively factor out or subtract those noisy signals from the lower layers' representation.
Leaving the lower layers with cleaner, more robust fundamental features.
Which is exactly what you want for good generalization.
Now, a really critical point the paper makes is that this correction process is local. This isn't the network throwing everything out and starting over.
No, not at all. It's fine-tuning. You can see it in the data. They compare the neuron weights before and after BFC kicks in, and the correlation is incredibly high, often over 0.9.
So the weights are just being nudged a little bit. It's a small adjustment.
A very subtle shift, not a revolution. And this locality has huge implications for one of the biggest theoretical frameworks out there today.
The neural tangent kernel, NTK.
Right. This is a direct counterargument to the idea that NTK can explain the full power of deep learning.
Because NTK is basically a linear approximation, right?
Mm-hmm.
It assumes the network is infinitely wide and stays very, very close to its random starting point.
Essentially, yes, the function is just evolving linearly. But if BFC is necessary for hierarchical learning, and BFC involves these continuous nonlinear adjustments that push the network far away from initialization,
then NTK can't be the whole story.
It can't be. The very fact that the correction is local means the network has already traveled a long way, non-linearly, to get those Bayes features in place. And the paper shows this. The final learned weights have a very low correlation with their random initial state.
So deep hierarchical learning, the kind we see in practice, is happening way outside the NTK regime.
It's a fundamentally non-linear feature learning phenomenon.
And they formalize this separation.
Yeah.
They show that non-hierarchical methods like kernel methods just can't solve these same problems efficiently.
That's the big separation result. They construct a class of problems, those high-degree polynomials again, where any kernel method would need an exponential number of samples, something like d to the power of 2l. It's just computationally infeasible.
Because they can't compose features. They have to model every single interaction explicitly.
Right, and then they show it empirically. The quadratic networks they study, which do use BFC, perform on par with ReLUs on CFAR10, but they absolutely crush optimized kernel methods.
Even things like the neural compositional kernel.
Trounce them in both speed and accuracy. It's definitive proof that the kernel view is missing this essential hierarchical component.
Okay, let's pivot a bit to the deep theoretical machinery they use to actually prove all of this. It starts with a specific network structure.
Yes, a generalized one, kind of like a ResNet or DenseNet with skip connections, but they use a quadratic activation function, z².
Which seems like a weird choice, but I assume it's for the proof.
It makes the proof tractable. It lets you formally show how features compose and interact. And as we just said, empirically, it works surprisingly well, much like ReLU.
Now, one of the biggest requirements in the theory is massive overparameterization, specifically quadratically sized. The width has to be huge. Why? Is this just to make optimization easy?
No, and this is a really key insight of the paper. It's not just about smoothing the loss landscape. Think of the massive width as providing a rich palette of building blocks.
A dictionary of features.
A huge dictionary. The overparameterization forces the network to learn a wide, diverse array of hidden features. Things like specific high-order monomials by 1 to the 4th, by 2 to the 4th, and so on.
So that when the higher layers start their forward feature learning, they have everything they could possibly need right there to choose from.
Exactly. It guarantees the necessary feature set is available for them to use and, critically, for BFC to then correct locally.
The training objective itself looks pretty scary. There's the standard loss, but also these regularizers with rank matrices, these K matrices. What's going on there?
That's the knowledge distillation part of the proof. The
Yeah.
network you're training, W, is huge and over-parameterized. The target network, G star, has a simple low-rank structure.
Okay.
The K matrices are there to make sure the knowledge learned by the giant W matrix can be distilled back down into that low-rank form. The regularizers basically force K transpose K to be a good low-rank approximation of W transpose W.
So it's a theoretical tool to bridge the gap between the learner and the target. But does this distillation cause BFC?
And that's the crucial clarification the paper makes. No, BFC is handled solely and automatically by SGD. It's just a natural consequence of simultaneous end-to-end training. The distillation is just there for the proof, to guarantee the final solution is close to the target. It doesn't generate the corrected gradients.
Got it. And there are two other theoretical tricks. One is this truncated quadratic activation.
Purely mathematical scaffolding. Using a truncated function gives you bounded derivatives, Lipschitz smoothness, all the nice properties you need to formally analyze SGD's convergence.
But not something you'd use in practice.
Right. They argue it's fine because real networks show self-regularization anyway, so the final result holds.
And the final piece of the theoretical puzzle, the information gap assumption. This seems critical.
It's the cornerstone. It's the assumption that explains why the correction can be local and efficient.
And the assumption is basically that as you go deeper into the network, the functions being learned contribute less and less to the final output.
Exactly. In practical terms, it means your early layers do most of the heavy lifting. They solve, say, 75% of the classification problem on CFAR 10. The deeper layers are just there to clean up the difficult edge case examples.
Which makes perfect sense. If the early layers were totally wrong, BFC wouldn't be a small local correction. It would have to be a complete rewrite of the network.
It would be a catastrophic change. But because the error that needs to be fixed is small, the correction can be local, subtle, and fast.
So if we pull this all together, the big takeaway is that deep learning's magic isn't just in its architecture, but in the training dynamic itself.
It's this continuous process of backward feature correction, enabled by simple, simultaneous SGD that prevents the early layers from making greedy, short-sighted mistakes.
It's what allows the network to actually use its hierarchical power without falling into the optimization traps that doom other methods.
And it all relies on having enough over-parameterization to create the features and on this information gap structure in the problem itself, which ensures the correction is always manageable.
You know, the implications of that information gap assumption are pretty profound. If you accept that early layers must solve most of the problem, and that BFC must be a local refinement for the hard cases.
It gives you a strong guiding principle for how to design architectures.
Right. And I have to wonder, think about how this idea is almost explicitly baked into some of our deepest models today, like transformers. You see all these techniques, layer normalization, residual connections, sometimes even explicitly downweighting the outputs of the final layers.
Yeah.
Is it possible that our best architectural innovations have been unconsciously driven by this theoretical need for a local manageable correction? That's something to really mull over.
A fascinating thought. The bridge between deep theory and engineering intuition.
This has been The Deep Dive. Thank you for joining us.